Okay, so now we're on to chapter 16, which is all about solutions. We talked a little bit about in chapter 15 about the properties of water and then the difference between heterogeneous mixtures and homogeneous mixtures. And now we know homogeneous mixtures can also be called solutions. And so now we're just talking about, more about them. The 16.1 are a lot of the qualitative properties, and 16.2 is going into some of the quantitative properties. So the first thing to look at is the factors that affect the rate of solution. And this is really important to talk about because one of the things that we did not get to do this year was talk about the factors that affect the rate of a reaction. That's a whole unit in AP Chem called kinetics. How can you speed up a reaction? And the good thing is that a lot of the factors that can affect the rate of any chemical reaction will also affect the rate of something dissolving. And they're also things that you have seen in real life. So I just labeled these three pictures A, B, and C. And then if we were in class, I would say, okay, so which one looks like it's representing agitation? And for those of you who don't know quite what that word means, it's basically mixing, stirring. So this is, of course, B. And so how does that affect the rate of dissolving? So the rate of solvation, that's a fancy name for dissolving. What has to occur for something to dissolve? We saw this back in chapter 15. You have to have attractions between solute and solvent. And what these do is they increase those collisions between solute and solvent. And that is where factors that affect the rate of solvation are very similar to the factors that can affect the rate of a reaction, because that's what you need for a reaction to occur. You need those reactant particles to actually collide. So if I agitate or I stir, this is, of course, dissolving sugar in water. That's what these three pictures are representing. If I stir the solution up, as in B, I increase the rate in which the collisions between sugar molecules and water molecules collide. And that increases the rate of solvation, the rate of dissolving. The next one is surface area. And so which one of these pictures is representing a difference in surface area? Well, that would be A, right? If you look at A, you have a sugar cube. If you have a sugar cube, right? So think about the sugar molecule that's way in the middle. It is not colliding with water until all the other sugar molecules dissolve. So a sugar cube will actually take a significant amount of time to dissolve in water, whereas if you just have crystallized sugar, it will go much quicker. And then, of course, that makes C, temperature, one factor. And yes, temperature will increase the collisions between the solute and the solvent. We know at a higher temperature, the molecules are moving more quickly, right? So the number of collisions will increase. But there's something else that's going on with temperature that's sort of a big deal. And that is you also have more energy. So at an increased temperature, you of course have more energy to overcome those, I'll just say attractions, because it could be many different attractions. So of course, in this example, sugar molecules are attracted to sugar molecules, water molecules are attracted to water molecules. And when you increase the temperature, you increase these guys' energy so they're able to overcome those attractions, and then they can be attracted to each other. Okay? And so those are very similar to a lot of the properties or a lot of the ways that we can increase the rate of a chemical reaction. So now let's look at solubility. So what is solubility? So we're not talking about whether something is soluble or is soluble. Now what we're really talking about is, well, how much? And so solubility is defined as the maximum amount. And it's typically in grams. It could be in moles, but then it's usually called molar solubility. So the maximum amount of solute that can dissolve in a given amount of solvent. And the given amount of solvent, it's usually like 100 grams of water. Not always, but it's typically 100 grams of water. So this, so if you look at the graph here, right? And so the graph shows a bunch of different chemical species, and the chemical species here show how their solubility is affected by temperature, right? And so we have a couple different words that can be used to describe a solution. An unsaturated solution, right? So think of unsaturated. What might that mean? It's when you have less than the maximum. The maximum amount of solute. It means you could dissolve more, right? If you take, a glass of water and you put in it a teaspoon of sugar and you stir it around, the sugar dissolves. If you take another teaspoon and you put it in and the sugar again dissolves, you have an unsaturated solution because you have less than the maximum amount. It could dissolve more. So then a saturated solution, right? So saturated, think of like a paper towel. When a paper towel is saturated, right? It means that's the maximum that it can hold. And a saturated solution is a solution with the maximum amount of solute dissolved. So that if you were to add another teaspoon of salt and sugar in, it wouldn't dissolve. It would just sink to the bottom and remain as a crystal. Okay, so no more can dissolve. Right? Sometimes you can see that when you go to Dunkin' Donuts or Mary Lou's and you get an iced coffee with sugar. And oftentimes there'll be sugar down the bottom that isn't dissolved. And, no matter how much you stir it, that sugar isn't dissolved. That could mean that you have saturated the solution. Okay? So let's look at the graph over here. So what happens to the solubility of KNO3 as the temperature is increased? So here's KNO3. You can see as the temperature increased, the solubility increases. Which, if you look at this graph, this is generally true, right? Which substance exhibits the least change in solubility as the temperature increases, right? If you look at this graph, I think you can see NaCl, right? NaCl just generally has a pretty stable solubility. The temperature does not necessarily change the solubility all that much. And I believe I changed this in your handout before I sent it out to KBr, because NaCl doesn't really change in solubility. So suppose that you added some solid KBr to a saturated solution at 20 degrees Celsius and warmed the mixture up to 40 degrees Celsius. What would happen to the added NaCl? So at 20 degrees Celsius, right? So let's say this is 20 degrees Celsius. Here's the saturated solution, right? If I were to add, I add some solid KBr. What I would see is that this KBr would sink to the bottom. Then what would happen when I increase the temperature to 40 degrees Celsius? I would see that the additional solid that I added would dissolve because the solubility is greater at 20 degrees Celsius is greater at 40 degrees Celsius than 20 degrees Celsius. So this is really summing it all up here. What is the relationship between the solubility of most compounds in water and temperature? And so you have seen this, I know, with dissolving things like sugar in tea and coffee your whole life. But of course, the solubility increases as the temperature increases. Right? And that's not true for every compound. You can see this YB, ytterbium, probably. Ytterbium sulfate there actually decreases, but for the most part, the solubility increases as temperature increases. So now the next two are asking about gases, and gases are very different than solids. So you're going to see a different relationship occur here. And when you think of the relationship between solubility of gases and temperature and pressure, think of soda. Think of what is a carbonated beverage? A carbonated beverage is where carbon dioxide is dissolved in water. So what happens to the solubility of that carbon dioxide as the temperature increases? And you guys probably know this, that it becomes flat. Well, what does it mean to become flat? It means there's no or less carbon dioxide dissolved. So with gases, it's exactly the opposite. There we go. The solubility decreases as the temperature increases, right? You want to keep your soda from going flat. You got to keep it in the refrigerator. And then what is the relationship between solubility? It's the solubility of gases and pressure, right? If you leave a bottle of soda open, that is decreasing the pressure because it's just atmospheric pressure. And we would know that that would then go down. So the solubility decreases as the pressure decreases, or you can think of it exactly the opposite. The solubility increases as pressure increases. That's why you have to leave the cap on the soda in order to keep that carbon dioxide dissolved. On the next page, you see a big data table that has a lot of data on this, and you can see some of the trends that we wrote about on the previous page. That in general, as the temperature increases, the solubility increases. You'll see that it isn't true 100% of the time, but for the most part, as the solubility increases, or as the temperature increases, the solubility increases, and you'll see that for the three gases down here, right? These guys are all gases. You will see that, the exact opposite is true, that as the temperature increases, the solubility of the gases decreases, right? These gases, do you see how their numbers are much, much, much smaller than the numbers for the solids? Well, yeah, because you know what these guys all are? They are all nonpolar. So what is the only intermolecular force? London dispersion forces. We know that those are very weak. So is oxygen very attracted to water? Hardly, not at all. Very, very, very little, which is why only a very small amount of oxygen can be dissolved in water, as opposed to salt. Here's salt, NaCl. A much greater amount of grams is able to dissolve in water. And this becomes really important. The amount of oxygen dissolved in water and the amount of carbon dioxide dissolved in water becomes really important in environmental applications, right? Marine organisms, animals like fish, need to breathe in oxygen that's dissolved in water, right? And carbon dioxide, one of our most important greenhouse gases, actually does dissolve in water quite a bit. And because of that, look at how big that is compared with the other two. And because of that, a lot of the carbon dioxide that we have put in the atmosphere since the beginning of the Industrial Revolution has been absorbed by the ocean. So we actually haven't felt the full effect. But what is happening to the ocean? the ocean is warming because of the greenhouse effect. And look at what happens. As the ocean warms, less and less carbon dioxide is able to dissolve in the water. This is an example of what's called a positive feedback loop. So as the ocean warms, less carbon dioxide dissolves in water. The carbon dioxide then goes into the atmosphere. That causes the atmosphere to warm. That causes the oceans to warm. That causes less carbon dioxide to enter into the atmosphere. So we talked about an unsaturated solution and a saturated solution. This is a weird one here, supersaturated solution, right? Just from the prefixes, you can sort of guess the definition of this, that a supersaturated solution is when you have more than the maximum amount. And you say, how can you have more than the maximum? Like, what isn't maximum mean the most? How can you have more than the maximum? Well, you have to do it very carefully. So you would heat up the solvent, then saturate it at that higher temperature, and then cool slowly. Right? It is, so you can see, like, here's the saturated, or if I go through these four, here's an unsaturated solution, right? You can see the orange solid down there, and look at the arrows. Most of the arrows are pointing up, which means they're dissolving. There's always going to be a process where particles are undissolving or recrystallizing. Both of those are happening at the same time. When they happen at the same rate, if you look at this picture, right, there's the same number of red arrows as black arrows. That's a saturated solution. We would say that this system is at equilibrium. And the fact that a saturated solution is in equilibrium becomes very important in AP chemistry. So then what could we do? Look and see how there's still some solid, right, undissolved or as crystal form on the bottom. Well, if I heat this up, heat and then cool, right, I could make a super saturated solution. Look at how much more orange that is. Once I have a super saturated solution, this is very unstable. And so any sort of disturbance will cause it to recrystallize. And a disturbance could mean literally just like bumping into the table, walking next to the jar that is holding this, or adding a seed crystal, adding just one little crystal of that solid. And what that will do is cause all of the extra dissolved solute to recrystallize and form, remember we talked about this, and form a precipitate. Okay. The last vocabulary word in this section before we get started on the math are miscible and immiscible. They are analogous to the words soluble and insoluble, but they're used for two liquids. Right? It doesn't really make sense if we say, like, is oil soluble in water or is water soluble in oil? Because they would, who does the dissolving, who is being dissolved? It would be a mutual relationship. So we use the words miscible and immiscible, right? Miscible would be two liquids with similar intermolecular forces, right? And immiscible, so what would immiscible mean? That would happen with two liquids with different intermolecular forces, right? So they wouldn't be attracted to each other, therefore they would not be able to mix. So a good example of this is water and ethanol. Right? Both of these have or are able to hydrogen bond, right? All of these have an oxygen bonded to a hydrogen. And so since they have similar intermolecular forces, hydrogen bonding, they're able to mix together really easily, right? This is, when you have like beer, wine, liquor, most of that is water. Almost all of the molecules that you are drinking are molecules of water, but mixed in there are molecules of ethanol, and there's no separation. It's evenly distributed because those two chemicals, those two molecules are miscible in each other. But an example of two liquids that wouldn't be miscible in each other are water and oil. Oil, there's many different types of oil, but oil is generally a whole bunch of hydrocarbons, so hydrogen and carbon together. And when you have this would be nonpolar, whereas water, of course, is very polar. And there's no attraction between those two molecules, right? Water is much more attracted to itself than it is to oil, so they're not able to mix. Okay, so just those two words, it's just vocabulary. They are just used instead of soluble or insoluble for liquids. Okay, so get your calculator out for 16.2, where we're going to do some calculations.